Right, so get this. Today we're diving deep, really deep, into something pretty mind-blowing.
Oh, yeah.
Using our sun, get this,
Okay.
as a giant telescope.
Whoa.
I know, right?
That's wild.
It's crazy. And I know you're all ears about this potential NASA mission that could, like, give us these super detailed images of exoplanet.
Oh, yeah.
Planets outside of our solar system. So let's just jump right in, shall we?
Let's do it.
We're going to be looking at some awesome research from the NASA Innovative Advanced Concepts Program,
Cool.
NIAC for short.
I've heard of that.
Yeah, it's really cool stuff.
So what's really cool is this all comes from like this real phenomenon called gravitational lensing.
Okay.
You know, and Einstein, he predicted it himself.
Wow.
Yeah, and basically, like supermassive objects, think our sun,
Yeah.
they can bend light with their gravity.
So, like, if the sun's gravity is pulling on everything, like even light, how do we see anything behind it? Does it just, like, blot out the whole background?
That's a great question.
Mm.
It's true that the sun's gravity does bend light, but it doesn't block out like everything. Think like kind of like a magnifying glass, you know?
Okay. Yeah.
It bends light rays, bringing them to a focus, but it doesn't make the object behind it like disappear.
Okay, I
Yeah,
see. So it bends the light around.
Exactly.
Okay, so that makes sense. But then how does this turn our sun into a telescope?
Right.
And how could we use it to see something as small and as far away as an exoplanet?
Okay, so this is where things get really, really cool.
Okay.
When light from a distant exoplanet passes by the sun's gravity bends that light.
Okay.
And it focuses it into a ring shape around the sun.
Okay.
And this ring, it's called an Einstein ring.
Oh, wow.
Yeah.
I've heard of those.
You know, picture a ripple in a pond, like spreading out after you throw a pebble in.
Yeah.
But instead of water, it's light.
Okay.
Pretty wild, right?
I can picture that.
Yeah.
So this ring of light is
Yeah.
like a magnified image of the exoplanet.
Precisely. And the magnification, oh man, it's incredible.
Okay.
We're talking being able to see details on a planet's surface from hundreds of light years away.
Really?
Yeah. It's like spotting a dime on the surface of the moon from Earth.
Wow, now that's some serious zoom.
Yeah.
But if the sun is our lens, like, where would we need to be to actually use this solar telescope?
Right. So for the magnification to work its magic, we'd need to send a spacecraft to a specific point in space.
Okay.
And it's called the Solar Gravitational Lens Focal Point.
Right.
You can think of it like the sweet spot where all those bent light rays come together.
And where exactly is this sweet spot?
Well, it's quite a journey, let me tell you.
Okay.
We'd be talking about roughly 550 AU from the sun.
Okay, now remind me, how far is that, like, in layman's terms?
Okay, so that's over 15 times farther than Pluto.
Wow, that is a trek.
It is.
Okay, so how do we even get out there?
Well, to get there, it requires some groundbreaking propulsion technology
Oh, of course.
and some really clever ways to shield the spacecraft from the sun's heat.
Yeah.
It's intense out there.
I bet.
You know, we're talking some serious next-level engineering to pull this off.
Okay, so let's just say, hypothetically, we managed to, like, you know, overcome these challenges
Right.
and park a spacecraft at this focal point.
Okay.
How would we actually take a picture using this whole sun as a telescope setup?
So it wouldn't be as easy as, like, snapping a photo on your phone.
Right.
Because of the way the SGL bends the light.
Okay.
The image wouldn't be a single snapshot.
Oh, okay.
It would be more spread out as a ring around the sun.
Interesting.
Yeah, so our spacecraft would need to carefully scan this Einstein ring, almost like tracing a giant faint circle in the sky.
So it sounds more like creating a cosmic mosaic than taking a picture.
It kind of is, yeah.
That's really cool.
It is.
But, like, how would we even see that faint light from the exoplanet when the sun is, like, blazing?
Right, so that's where another mind-blowing piece of technology comes in.
Okay.
It's called a coronagraph.
Okay.
Think of it like a tiny, perfectly shaped mask.
And it blocks out the sun's blinding glare, allowing us to see that faint starlight hiding behind it.
Okay.
But to make this work, this coronagraph, it would need to be incredibly precise,
Right.
blocking out 99.9999% of the sun's light.
Wow.
Yeah, talk about impressive light blocking.
That's incredible. But let's get back to the image itself. Like, what kind of resolution are we talking about?
Right.
Could we really see surface details of exoplanets?
Absolutely. With the SGL, we could potentially capture images with enough resolution to see continents, oceans, and even signs of cities.
Really?
Yeah. On an Earth-like exoplanet, we're talking about megapixel images of alien worlds.
Megapixel images of planets hundreds of light years away. I'm starting to see why this SGL mission is causing such a stir.
It's pretty remarkable.
It is.
And there's even more to it.
Oh, there's more.
Yeah. Not only could we capture, like, these stunning visuals,
Right.
but the SGL would also allow us to analyze the light from the exoplanet to learn about its atmosphere.
Wait, so we could, like, sniff out the air of an alien world from hundreds of light years away?
Essentially, yes.
Tell me more.
All right, so now we're getting into the realm of spectroscopy,
Hmm?
which is basically like taking a planet's fingerprint by splitting its light into different colors.
Okay.
You know, similar to how a prism splits sunlight into a rainbow.
Oh, yeah.
Yeah, exactly.
Okay.
Oh, okay.
So by looking at the rainbow of an exoplanet's light, we could figure out what its atmosphere is made of.
That's the idea.
That's amazing. Could we even find, like, signs of life that way?
Exactly. By analyzing the light, we could look for specific gases that are like strong indicators of life as we know it, things like oxygen or methane.
Oh, wow.
You know, it's like being a cosmic detective searching for clues in the light itself.
This is blowing my mind. I never imagined we could use the sun to unlock so many secrets about distant worlds.
It truly is a game changer, and we've only just scratched the surface here. There's so much more to explore with the SGL, from the technical challenges to the mind-boggling possibilities it opens up.
I can't wait to hear more.
Oh, we've got a lot more to discuss, trust me.
This is going to be good.
It is.
All right, well, let's take a quick break, and we'll be right back with more on this amazing solar gravitational lens.
See you in a bit.
Okay, I'm already, like, hooked on this idea.
I figured.
But I have to ask,
Yeah.
like, what's next for this research? Where do we go from here with this solar gravitational lens?
So this NIAC study, the one we're talking about,
Right.
it's like laying the groundwork for some seriously ambitious missions. There's a lot of possibilities being explored right now.
Like what? Give me, like, a sneak peek into the future of these SGL missions.
Okay, so for one, imagine this. Instead of just one spacecraft at that focal point, a whole swarm of smaller, like, interconnected probes working together.
A whole fleet of mini-sun telescopes. Why would we need so many?
So think of it like having, like, multiple eyes in the sky.
Okay.
This swarm could scan different parts of the Einstein ring at the same time,
Okay.
speeding up that whole imaging process.
Yeah, that makes sense.
And plus, like, if one probe glitches out, the others can keep going.
Oh, well, that's smart.
You know, built-in redundancy.
So it's like having a backup system, but out there, millions of kilometers away.
Exactly.
That's really cool.
It is pretty cool.
Are there any other, like, wild concepts on the table?
Yeah, there's another one that involves tethered spacecraft.
Okay.
So imagine, like, two spacecraft connected by a long cable,
Okay.
like a space tightrope.
Oh, wow.
Yeah.
That's pretty wild.
And this tether, it could provide stability
Okay.
and help with, like, fine-tuning the spacecraft's position, which is super important for those precise Einstein ring scans.
A tethered spacecraft doing a cosmic dance 15 times farther away than Pluto. This is some next-level space exploration.
Yeah, it is.
But realistically, how long until we see an actual SGL mission launch?
So, like any ambitious space project, it really comes down to, like, technological breakthroughs and funding.
Of course, yeah.
There's a ton of work to be done,
Yeah.
but the potential payoff is enormous.
Oh, I can imagine.
I'm optimistic that we can see a mission launch within a few decades, though.
A few decades to potentially see another Earth in such detail, I can wait.
Yeah.
But besides the obvious challenges like the distance, the sun's heat, what other hurdles would this mission need to clear?
One of the biggest is navigation.
Oh, right.
Pinpointing a spacecraft with that level of precision at such a crazy distance, it's not easy.
I bet.
We're talking about taking into account the gravitational pull of planets, the pressure from sunlight, even tiny wobbles in the sun itself.
Wow.
It's a lot.
So it's not just about getting there.
Right.
It's about staying in that exact spot, potentially for years.
Yeah, while it scans the Einstein ring.
Wow.
And remember, the spacecraft systems need to survive the harsh conditions of deep space for decades. We're talking about developing super reliable radiation-resistant technology that can operate flawlessly for an incredibly long time.
This sounds like it would push the limits of engineering and our understanding of the universe.
This kind of mission would be about more than just snapping a cool picture.
Yeah.
It'd be about expanding the boundaries of human ingenuity and what's possible in space exploration.
I'm starting to feel that same, like, sense of awe and possibility that we had with the Apollo missions.
I get that.
But before we go any further, let's get back to the listeners' interest in exoplanets.
Right.
Specifically, like, Earth-like ones.
Okay.
Where would we even start looking for one?
Well, we're lucky to live in a time where we're discovering exoplanets at an astonishing rate.
It's true, yeah.
There are already missions like TESS and the James Webb Space Telescope
Right.
actively searching for planets that could potentially support life.
So those missions are like the scouts,
Yeah.
scoping out the best targets
Yeah.
for our future SGL mission.
Exactly. They're gathering crucial information about these distant worlds,
Okay.
helping us pinpoint the most promising candidates, ones that have the right ingredients for life as we know it, like liquid water, a suitable atmosphere, a stable climate.
So it's a two-pronged approach.
Yeah.
We use these other telescopes to find the most, intriguing exoplanets.
Right.
And then we send our SGL mission to get that incredibly detailed close-up.
That's the grand plan.
I like it.
Yeah, we're living in an era of incredible discoveries, and the solar gravitational lens has the potential to completely revolutionize our understanding of exoplanets.
Okay, so we've talked about finding these Earth-like exoplanets
Yeah.
and sending a spacecraft to the SGL focal point.
Right.
But let's zoom in on the data collection process.
Okay.
How would we actually capture an image using the sun as a lens?
So imagine it like this. The light from the exoplanet, bent by the sun's gravity,
Right.
it forms that Einstein ring.
Okay.
And within that ring, that's all the information we need to reconstruct an image of the planet.
So it's like a giant cosmic jigsaw puzzle.
Yeah, a very faint and complex one.
I bet.
Our spacecraft at the SGL focal point would need to act like this tiny, incredibly sensitive light detector,
Right.
meticulously tracing the entire Einstein ring,
Wow.
point by point,
Okay.
collecting data about the light's brightness, its color,
Right.
and even its polarization.
Hold on. Polarization.
Yeah.
Like polarized sunglasses. What does that tell us about an exoplanet hundreds of light years away?
It's all about the direction of the light waves.
Huh?
Think of light as a wave that vibrates.
Yeah.
Polarization tells us the direction of that vibration.
Okay.
Light can be polarized in different ways as it interacts with things, like bouncing off a planet's surface
Okay.
or passing through clouds in its atmosphere.
So we're adding yet another layer of information to our cosmic jigsaw puzzle.
Exactly. And this is where things get really exciting.
Okay.
By combining what we learn from polarization with the spectroscopy data we talked about before, we can get an even more detailed understanding of that exoplanet's environment.
We're using all these different properties of light.
Mm.
Brightness, color, polarization,
Yeah.
the spectrum to build a multidimensional picture of a distant world.
Yeah.
It's like we're holding a piece of that planet right here in our hands.
It really is. And it all comes down to the incredible power of the sun's gravity,
Yeah.
used in a way we never imagined before.
Right?
We're on the verge of being able to study exoplanets in a way that was once considered science fiction.
This is blowing my mind.
Yeah.
I never thought we could learn so much about a distant planet just by analyzing the light that passes by our sun. But let's be real for a sec.
Okay.
There has to be a downside to all this, right?
Well, sure.
What are the potential drawbacks of this mission?
Well, like any ambitious space project,
Right.
the biggest hurdles are going to be time and resources.
Yeah.
It would take a massive investment of both to make this kind of mission a reality.
That's true.
And there's always a risk that even after all that effort,
Hmm.
we might not find what we're looking for.
You mean we might scan a planet and not find any signs of life?
It's a possibility.
Oh, okay.
But even if we don't find aliens waving back at us,
Right.
the knowledge we gain along the way will be invaluable.
Sure.
We'll learn so much about the universe, about exoplanets, about the possibilities and limitations of life itself.
It sounds like a win-win either way.
It kind of is.
We either find evidence of life beyond Earth, which would be huge,
Oh, yeah.
or we learn a lot about the universe in the process, which is still incredibly valuable.
Absolutely. It's about pushing the boundaries of human knowledge and exploration.
I agree.
This mission would be a testament to our curiosity
Yeah.
and our desire to understand our place in the cosmos.
It's a story of human ambition and ingenuity, a story that's still being written.
Yeah, for sure.
I can't wait to see what the next chapter holds. But before we get ahead of ourselves,
Right.
let's step back and really consider the significance of using the sun as a telescope.
It's a truly remarkable concept, you know?
It is.
Using the very object that illuminates our world to study distant worlds.
Right.
It's both, poetic and groundbreaking.
It makes you realize how interconnected everything in the universe really is.
It really does.
But speaking of interconnectedness, let's talk about the data itself.
Okay.
How would we take all that raw data from the SGL mission
Yeah.
and turn it into something we can understand, something that like reveals the secrets of a distant planet.
So that's where the power of computation and data analysis comes in.
Of course.
We'd be collecting a massive amount of information about the light from that exoplanet.
Yeah.
And we'd need to process it, filter out noise, and then piece it all together to form a coherent image.
It sounds incredibly complex.
Oh, it is. But thankfully, we have brilliant minds in fields like computer science, astrophysics, image processing, who are constantly developing new techniques to tackle these challenges.
So it's a true, like, interdisciplinary effort.
It is.
Bringing together experts from all sorts of fields.
Yeah.
It sounds like this mission would be a catalyst for innovation.
Absolutely.
Not just in space exploration, but in other areas as well.
Oh, totally. The potential ripple effects of this kind of mission are immense.
Wow.
It could lead to advancements in computing, optics, materials, science.
Right.
Who knows what else?
It's like throwing a pebble into a pond and watching the ripples spread out in all directions.
Exactly. And that's the beauty of scientific exploration.
Yeah.
It often leads to unexpected discoveries and advancements that benefit all of humanity.
It's a reminder that knowledge and innovation are like interconnected.
They are?
And that by pushing the boundaries in one area, we can create positive change in many others.
Absolutely.
But for now, let's focus on the specific knowledge we'd gained from an SGL mission.
Okay.
We've talked about capturing images, analyzing atmospheres.
Right.
But what other secrets could we unlock about these distant worlds?
Well, with the SGL, we could potentially study weather patterns on an exoplanet,
Really?
track the movement of clouds, even observe seasonal changes.
So we could see, like, alien storms brewing. Or maybe even witness the changing colors of an alien autumn.
It's not outside the realm of possibility.
That's so cool.
We could also map the surface of the exoplanet in unprecedented detail,
Okay.
identifying geological features like mountains, valleys, maybe even active volcanoes.
It's like we're holding a magnifying glass up to an alien world,
Yeah.
peering into its deepest secrets.
And the more we learn about these distant worlds, the more we understand about our own planet and the delicate balance that makes life possible.
It puts things into perspective, doesn't it?
It does.
It makes you realize just how precious and unique our own planet is, but it also makes you wonder, what other Earth-like planets are out there, waiting to be discovered?
That's the question that drives us, isn't it? The desire to know if we're alone in the universe or if there are other worlds out there teeming with life.
It's a fundamental question that has, like, haunted humanity for centuries.
I agree.
And the solar gravitational lens might just be the key to unlocking the answer.
It's a tool of unprecedented power, a tool that could rewrite our understanding of the cosmos and our place within it.
It's a tool that embodies the spirit of exploration, the human drive to push beyond the known and venture into the unknown.
And who knows what wonders await us on that journey.
You know, it's incredible to think that we could be on the cusp of, like, this whole new era of exoplanet exploration.
I know, right?
And all thanks to our own sun.
Yeah, it's pretty amazing.
But I keep coming back to this whole idea of using the sun as a magnifying glass. It just seems so counterintuitive.
It does, doesn't it?
Like, we think of the sun as this, you know, incredibly bright object that illuminates our world.
Yeah.
Not something that, like, helps us see other worlds.
Right, but that's the amazing thing about gravity.
Yeah.
It can, like, warp and bend light in a way that it acts as a natural lens.
Okay.
Yeah.
I'm starting to wrap my head around the concept.
Good.
But I'm still a little curious about the practicalities.
Yeah.
So let's say our spacecraft reaches that sweet spot, 550 AU away.
Okay, yeah.
And it starts scanning the Einstein ring of, like, a promising exoplanet.
Right.
What kind of data is it actually collecting?
So the data itself, it's super complex.
Okay.
It's not just a, like, simple picture.
Right.
It's this huge amount of information about the light coming from that distant planet.
Okay.
So we're talking about measuring the brightness, the color of the light, but also something called polarization.
Polarization.
Yeah.
Like those polarized sunglasses that, like, reduce glare.
Exactly.
What does that have to do with exoplanets?
So think of light as a wave that vibrates,
Yeah.
Polarization tells us the direction of that vibration.
Oh, okay.
And light can be polarized in different ways depending on how it interacts with matter.
Okay.
For example, light reflecting off a liquid ocean would be polarized differently than light bouncing off a rocky surface.
Oh, so by analyzing the polarization of the light, you could figure out what the surface of an exoplanet is like.
Exactly.
Wow.
We could differentiate between oceans, continents, ice caps.
Yeah.
maybe even vegetation.
Yeah. That's crazy.
It's really cool. It adds another like crucial piece to the puzzle
Yeah.
of understanding that distant world.
This is incredible. It's like we're building a multi-layered high-definition image
It is, yeah.
of an exoplanet from hundreds of light years away.
Yeah.
But how do we even make sense of all that data?
Right.
It must be like a massive amount of information to process.
Oh, you're right. It's a huge computational challenge.
Yeah.
But that's where the magic of data science and like advanced algorithms comes in.
Yeah.
You know, we have some brilliant minds working on developing techniques to sift through all that data, filter out noise,
Right.
and piece together a coherent picture.
So it's not just about capturing the light.
Right.
It's about like deciphering the secrets hidden within that light.
Right. Precisely.
Yeah.
And it's not just about creating like a visual image.
Okay.
Remember, we can combine this imaging data with the spectroscopy data we talked about
Right, yeah.
to get an even more complete picture of the exoplanet.
So we're essentially using the sun's gravity to create a virtual laboratory,
It is, yeah.
allowing us to study like alien worlds
Yeah.
in a level of detail we never thought possible.
It really is a testament to the ingenuity of scientists and engineers. You know,
It is.
we're constantly pushing the boundaries of
Yeah.
what's possible, using the laws of physics and technology to unlock these secrets of the universe.
I'm in awe of the possibilities. I really am.
Mm-hmm.
But amidst all this like scientific wonder, I have to ask,
Yeah.
why go to all this trouble?
Right.
Why spend decades and vast resources
Yeah.
to study planets we may never even visit?
It's a question every space explorer has pondered.
Right.
I think the answer is deeply rooted in our nature as humans.
Okay.
You know, we're inherently curious,
Yeah.
driven by a desire to
Yeah.
to understand our place in this like grand scheme of things.
It's about pushing the boundaries of human knowledge and like seeking answers to those age-old questions.
Absolutely.
Are we alone?
Right.
What other worlds are out there? What does
Yeah.
it even mean to be alive in this vast and mysterious universe?
Exactly. The search for life beyond Earth is a profound endeavor.
I agree.
And the solar gravitational lens gives us this unprecedented tool to pursue that search.
And even if we don't find like definitive proof
Right.
of extraterrestrial life, the journey itself will be worth it.
Oh, totally.
We'll learn so much about the universe, about the diversity of planets, about the conditions that make life possible.
Every piece of knowledge we gain expands our understanding of ourselves and our place in the cosmos.
Yeah.
It's a legacy
It is.
that will inspire generations to come.
You know, it's been an incredible journey exploring this mind-boggling potential
It has.
of the solar gravitational lens.
For sure.
It's made me realize just how much is still out there waiting to be discovered.
It's truly a testament to the boundless possibilities of science and the enduring human spirit of exploration.
And to our listener, we leave you with this.
Okay.
Imagine seeing a detailed image of a distant planet,
Yeah.
maybe even an Earth-like world
Right.
with oceans, continents,
Yeah.
who knows what else.
Yeah.
How would that change your perspective on our place in the universe?
It's a question worth pondering as we continue our collective journey of discovery.